Hi everyone, it's me, and we're going to try this video thing to see if this actually works today. I tried it twice yesterday and erased it every time, so hopefully this works out okay. Today we are going to be talking about vectors. You may have heard me mention vectors already in class when I drew something on the board for courses that looks something like that. This little line here means that that object is in fact a vector. How does this apply to what we're doing? Well, a vector in physics is a physical quantity that has both direction and magnitude, or size. For example, if you think of last season in physics, we have the velocity, right? The acceleration, and actually the displacement as well. So, velocity, when you say something is, if we give it this, 3 meters per second, right? That is the magnitude of this vector, but it is not defined yet because we've just defined the magnitude of this vector. If, however, we decide to call it positive 3 meters per second, we have then defined this vector to be in the positive direction. Notice that I took away the arrow when I defined a direction, right? So this means that the size of this vector is 3 meters per second, the magnitude, without a direction, which is why the arrow is still there. And then for here, I've defined direction, so now the arrow is down, and now we know the velocity is positive 3 meters per second. Same thing with acceleration. If we say that the acceleration is negative 1, sorry, not negative, without the negative, right? Because I just said that with if you include direction, you don't need this little arrow. So we'll call this 1 meter per second squared, right? That is the magnitude, the size of this vector for the acceleration. And then if we say that the acceleration is negative 1 meter per second squared, that tells us the direction of this vector. And then the same thing for displacement, right? So there's the arrow. We can say this thing is 50 meters, the magnitude of this vector. So whatever it is, it traveled 50 meters. And then we can say that the displacement is, let's say, positive 50 meters. Okay, now we've included direction, we've taken away the arrow. How does this apply to you? Well, if you think about it, we had this forces, right? So when we asked for the sum of the forces, right, then you have to break up whatever your object of interest is, or whatever the force is being exerted on your object of interest, into the x and y vectors. And so let's say we had some sort of object with these vectors on it, whatever, and we'll call this force A on O, force B on O, force C on O, and then force D on O. Right? So the sum of the forces, sum of the force vectors in the, let's say, the x direction for now, will equal force B on O plus force C on O. Notice I've left these in here, right? That's because we haven't defined a direction. If we have our axis, let's say, be like this, we'll call this plus x, and we'll call this plus y, then we know that both of these are in the positive direction, so we can now put in FB on O plus FC on O. Right, so this would be for the sum of the forces in the x direction. I've taken away the arrows, I've decided on their direction. You'll have to pardon me, we're going to jump up here to do the y. So if we look at the sum of the forces in the y direction, right, we have force, what is it, force A on O plus force D on O. And notice both of these are positive because I haven't defined direction. But then we look at our axis and see, well, force A on O is pointed up, and force D on O is pointed down, so force D is negative, force A is positive. So now the sum of the forces in the y direction are equal to positive force A on O plus negative force V on O. Okay? So this is how you would apply this to our usual mathematical representation of forces, the sum of the forces on an object. Notice that I broke it up into y and x, right? That's because you cannot add these vectors to each other. They are in two different directions, okay? And this will become more important later when we have a vector that goes off at an angle, right? So you can exert a force at an angle, not in the x or y direction, but it essentially has the effect of exerting two forces, one in the positive direction and one in the negative direction. But we'll look at that in a little bit. So why am I telling you this? What's the point of this? Well, what I'd like to show you is how we will use this for our force diagrams. So we'll move on. So when we have, let's say we have an object resting on a table. So here's our, whatever the object, we'll call it a rock. This is a rock, and this is a table. Alright. The rock will be our object of interest. Okay. And so now that we know our object of interest, we can set up our force diagram. We know that the objects interacting with our object of interest are the Earth, always, as long as you're on Earth, of course, and the table. So for our force diagram, let's use some of the cool features of this program. I can draw a straight line here. So right now I'm setting up my x and y axis. Okay, this will be our positive y, this will be our positive x. And so if we set up a force diagram for this, then we have our object of interest, the rock, not the wrestler, just the object. And we have, let's say, I don't know, let's say the Earth exerts a force of 5 newtons on the rock, right? So now, since we have this grid pattern here, like you had, or like you will have on the quiz tomorrow, then we can use this grid to define the magnitude of our force vector, right? So if this is 5 newtons, the Earth exerts 5 newtons on the rock, then we can count, let's say, 5 squares. We can define sort of one of these squares to equal 1 newton. Okay? So each one of these squares is 1 newton, so we want to draw an arrow that is 5 newtons. So here we go. We got 1, 2, 3, 4, 5. And so now we use this grid to add a little bit of quantitative data, numerical data, to our force diagram. We'll do the same thing up here. Since this object is in equilibrium, we know that the force exerted upward is the same as the force exerted downward. It's balanced, so 1, 2, 3, 4, 5. And so now I've defined the magnitude of these vectors. We'll define them, of course. We'll give them their labels. So force table on rock, force Earth on rock. Sorry, capital E. Right. So there you have it. So we've used our squares, our blocks in the background, to define the magnitude of each of these vectors, or to help us define. And of course, this is in equilibrium, so there's 5 newtons as well. So, right, moving on then. So, again, why is this important? Well, we're not always going to have a scenario where the external forces being exerted on our object are going to be up and down and left and right in the positive, in the x and y direction. So what happens when those objects are in the diagonal, on the diagonal? Well, before we go to that, what I would like to do is talk a little bit about adding vectors. So what does it mean to add a vector? So let's say we're given some sort of vector. We'll have one vector be 3 or 4 blocks, let's call it. So this vector is 4 blocks long. And we'll have another vector that is, we'll say, 2 blocks long. Alright, so let's call this vector B, and let's call this vector A. So if I asked you to add vector B to vector A, the way you would do it, if you for this, it's sort of simple. You can kind of figure it out. Essentially, you use something called the tip-to-tail method. Tip-to-tail method, where you put the two vectors side by side. In the case of addition, vector addition, it doesn't really matter which one you put first. You can put B behind A, or you can put B in front of A. I'll put B in front of A, so I'm going to draw a little, this will be our vector B. And then you draw a vector going from the tail, or I guess I should call it tail to tip. You draw a vector going from the tail of one to the tip of the other. So this red vector here is now A plus B, is the vector A plus B. We should put in, as I think about it, our little vector symbols, right? Because these are in fact vectors. And this would be one big arrow across the two of them. So this is our vector A plus B. Okay? Now, what about if we were to add two vectors together that were not in the same axis? So the x and y axis. And this is why you can't just add numbers together when you're going to add vectors. Because, so let's say we have one that is, instead of in the left and right, or x direction, let's say it's 4 in the y direction. Okay? And let's say it's 3 in the x direction. We'll draw it down here. We'll draw it over here. So now we have vector A, which is up, and vector B, which is to the right. So let's do the same thing. We'll take the tip of one and the tail of one and attach it to the tip of the other. It doesn't matter which. You can try both ways, and you'll see that you end up with the same resulting vector. So let's say, let's put the tail of A onto the tip of B. So B we said was 3, and A we said was 4. 1, 2, 3, 4. And so now the resulting vector, again, would be from the tail of one to the tip of the other. And so we now have vector B, vector A, and vector A plus B. Wow, I'm awesome. Alright, so there you have it. So this is how you add vectors, okay? Now similarly, if you can add vectors, you can subtract vectors. How does this work? Well, let's go to a new page. Okay, so let's start with the same way. We've got two vectors. Let's say we've got our same ones, A and B. And B. Let's make this 2. Why not? So A is 3, B is 2. The magnitude, rather. And so how would you write A minus B? Now in this case, A minus B and B minus A are different. What you'll end up doing is you, rather than doing A minus B, you actually do A plus negative B. So when I say negative B, I mean we take B and flip it around. So rather than having A and B next to each other, what we'll do is we'll have A, which is 4 blocks, 1, 2, 3, 4, and negative B, which will be the opposite. So you flip B around, and we add it to this. So what happens is B cancels out part of A. And so if you do the same thing where you draw a resulting vector from the tail to the tip, you end up with this smaller vector. Okay? And so now this vector here is A minus B. If this is A and that's B. Sorry. This is A, this is B. And so now the question is, why is B minus A different? Well, take a look. So if we do again, we have b, which is 2 in this direction, and you add negative a, which is 4 in this direction, and you draw the resulting arrow from the tail of b, of the first one. So this is b, this is a. If you do the same method we did, draw from the tip of the tail of the first one to the tip of the second one, it's not going to be this way anymore because we're going from here to here. So it's actually going to be this way. Sorry, didn't have the straight line function on. So notice that b minus a is actually the opposite of a minus b. This is b minus a, right? So that's how you subtract. You don't necessarily subtract, but you add the negative of you add. So instead of doing b minus a, it would actually be b plus negative a. And the same thing goes for when you're adding vectors or subtracting vectors at an angle or not in the same direction. So if we had, I guess we're doing these in red. We had this vector, which is 1, 2, 3, 4, 5. We'll call that vector A. And we have this vector, which is 3 to the right. This will be vector B, vector A. Then, in this case, A minus B, otherwise known as A plus negative B, would be the same thing. You would take A, draw A is fine. 1, 2, 3, 4, 5. And attach to the tip of it negative b, which is 3 to the left. So this will be 1, 2, 3. Oops. I have to pardon my little mistakes. I'm still not quite used to this program yet. So now you end up with this vector that goes again from the tail to the tip, and it is thusly. Okay? So that will give you, this is how you subtract in you subtract vectors. So what does this have to do with anything? Alright, so now let's look at an example force diagram that doesn't necessarily have the forces all in the x or y direction. I don't know why I made that so short. So now we have our axis. We'll call this positive x. We'll call this positive y. And let me just say that y doesn't have to be up. Positive y doesn't have to be up, and positive x doesn't have to be to the right. You're allowed to make it however you want. So let's say that we've got some force diagram that looks like this. We've got our object of interest, whatever this is. We'll call this O. And let's say we've got one force being exerted down, 3 blocks. One force being exerted to the right, 4 blocks. And one force being exerted at an angle, let's say like this. So, like that. And we'll call this F A on O. This will be F B on O, and this will be F C on O. So how do we figure out? So my question for you is this an equilibrium? Okay. And much the same way that we used the vectors, we added vectors together to have a resulting vector, we can also pick the vectors apart to have a resulting vector. So in reality, there's something up here. Let's get that out of the way. So what we can do, this is object O, what we can do is we can break this vector up into what we call its component vectors. Clear this out too. Need more space. So we can break it up into its component vectors. So when I say it's component, I mean the two vectors that add up to give us this resulting FA on O. Okay? And so I'll let you think about it a little bit. So you can pause now and think of how we will break this up. Really pause, I mean it. Okay, I'm assuming you've paused by now. So what we do is we can look at, and this is why I'm doing this on this grid paper, because we can see, okay, so it goes to the left, 1, 2, 3, 4. So the first component of this vector is going to be this way. And the second component, it goes up 1, 2, 3. You can draw it here coming from the center so that you don't have to move it later, or you can draw it here to make it easier to see where it is and then just move the vector over. But for now I'm going to draw it like this. So now what we've done is we've broken FA on O into two components. We will label these components with a label, with a name. This will be Fx, right, the x component of A on O. And this will be F, you can guess, Y, A on O. So this is the y component of A on O because it goes in the y direction, and this is the x component of A on O because it goes in the x direction. And there you have it. And now that you've broken it up into its components, you can see that the y component of A on O is it balances out FC on O, and the x component of A on O balances out B on O. Okay, that B out. So this is actually in equilibrium. Even if these forces are just components of this one, if there's only three objects interacting with it, you're allowed to break up components that are not in the x and y direction into component parts. You can add forces, so you can break up forces into component parts so that they're easier to solve. So why don't we take a look at another example, and I'll let you think about this. Those of you that are actually here watching this, I appreciate it. We'll go over this in class tomorrow, and you can look smart in front of all the people who didn't watch the video, if anybody watched the video, because I know it's kind of late, but I appreciate you waiting because it took me a while to get this thing made. So the force diagram that we're going to draw will look like this. An object in the middle, obviously, this is our object of interest. Let's say the force diagram looks something like this. We will have a upward force, we will have a leftward force, 3. We'll have a downward force of 3. And we'll have a force over at an angle of, let's say, like this. And so what I would like you to tell me is, first of all, what is the, in what direction is the unbalanced force, if there is any. And obviously, what are the components of each of these forces? You might want to label these. Tell you what, I'll label them for you because I'm nice like that. We'll call this force A on O, force B on O, force C on O, and force D on O. Alright? So, what are my other question for you now is, what are the components? Components of B, object B, or the force exerted by object B. And that's basically it. So is there an unbalanced force, and what are the components of B? Alright? And, lastly, as a bonus, describe a situation that can be, that would have a force diagram that looks like this. That's force diagram. Alright, I hope you enjoyed the video. I certainly enjoyed making it and playing with my new toys. It was awesome. And I'll see you in class tomorrow. I hope you all like it. Bye.